In this video, I'm going to run through a few examples of how you can calculate the average voltages or the root mean squared voltages, the RMS values, for various signals that you might measure on an oscilloscope. To be able to do the examples, you do need to remember how to integrate, so it's worth just refreshing yourself on how to integrate basic functions, including a little bit of trig, like how you can integrate a sine wave and that sort of thing. So you also need to know the equations for mean values and RMS values. So I'll start here with the average value. So you might want to refer back to the PHY 1002 course, and if you go to the week 5 material, you should see the formulae and the theory and the explanations there. So here you can see that the mean value, if you have a function of continuous values, will be equal to the area, that's the area under the function. So if you graph the function, you can measure the area underneath between two x values, and the mean value will be that area divided by the baseline. And what it means by the baseline is the spread in x values. So with some of our waveforms, it's possible to use this simple formula and just calculate an area and divide it by the change in x. So there are sometimes some ways that you can do that when you have waves that are triangular or square, for example. In other cases, when you have sine functions, for example, then you will always have to use this integral form of this equation. So in this case, in order to work out the area, you need to integrate the function between the two values and then divide by the spread in the x values. So in some cases you can use both methods, and in certain cases you can only use the integral form. So I'll just run through a few different examples. So here, this is known as a sawtooth wave, so you've got these little triangles, and if you want to work out the average voltage of this signal, then you can just take one of these points, one of these triangles, or one of these teeth, yeah? And if you work out the average of this shape, then you are working out essentially the average of the whole waveform. So let's just put a few details onto this sketch. So we'll say that this will be our ground point. So this, we're measuring everything relative to 0 volts on this diagram here. Let's give this, let's see, a peak to peak, or an amplitude of 5 volts. And this is defined as one period t, and we'll say in this case t is equivalent to 10 milliseconds. So in order to work out the mean value, we can either use the area divided by the change in the x. In this case, the x-axis is the time axis, so we can say change in t. Now this is an easy equation to use in our case because, as I say, you want to work out just the average of one of these triangles, and then that tells you the average of everything. So if this is 5 volts and this is 10 milliseconds, then the area of a triangle, so all of the stuff on the inside, you should know is equal to a half the base times the height. And so that's our area here, and then we need to divide through by the change in time. So a half times the base, which is 10 milliseconds, multiplied by the height, which is times 5, and this is then divided by the change in time is equal to the period t, so that's 10 milliseconds. So if you do the maths here, you can see my 10 milli and my 10 milli cancel, and I end up with 5 divided by 2, which gives me 2.5 volts. So that's a really easy calculation to use this equation here. Now, it is still possible for me to work this out using the integral notation. So if I want to do that, again, I take one period, which is t, which is equal to 10 milliseconds, and this is equal to 5 volts. Now, the equation states that I now need to integrate between 0 and 1 period t of the function v dt. So we would usually write the general form where this is y, the function y in terms of x, but in our case the y-axis is v and the x-axis is t. So this is my general formula. So now we need to know what's the function, what is v in terms of t. Well, this here, along this line, the function is a straight line. So we can use the straight line equation y equals mx plus c. Now c is the y-intercept, so at x equals 0, where does this intersect? Well, this is at 0, so this point is 0. So the c value is going to be 0. So then we just get y equals mx. As I said before, in our case the y-axis is voltage and the x-axis is t. So I actually get v equals mt, and m is the gradient. So we know that the gradient is equal to the change in y over the change in x, dy by dx. So in this case, in one period, the change in y is 5 and the change in x is 10 milliseconds. So that gives me my expression for v, which is equal to 5 over 10m times t. And so that is equal to 500 t. So this is just a value that I can now plug into here. So my equation was the mean is equal to 1 over t, t0 v dt. So t was 10 milli, this is 10 milli, this is 0, this is 500 t dt. So if I integrate this, I get 10m and minus 0 for when I plug in this value here, and then this will go with one of these, and this will give me 2.5 volts. So it's exactly equal, even though the method is a little longer, it's still equal to the other value that we found by using the area. So let's take a look at another example. In this example, we now have a square wave, so I'll add some values to this. Let's say now this is 10 volts. Again, ground can be at this level here. This is 5 milliseconds, 5 milliseconds. And one period would be represented like this. So the mean value is equal to the area over the base. So in this case, we calculate the total area under the function. We have nothing here, so we just need the area of this square. So that is an easy calculation. We have 5 milli times 10, and this, don't forget, we're dividing this by the entire base. Yeah, so it's divided across 10 milli. So here we have 50m over 10m, and we end up with 5 volts being the average. If you divide through by 5, then you will get an incorrect value. So your value will be too high. So be careful with that. It's possible to double check this because we can now calculate this another way. Your equation is this one. Within our one time period here, we actually have two different functions for the voltage V. So here in the first part between, if we take this as 0, then between 0 and the first 5 milliseconds, v is equal to 10. So we have that as the function. But in the second part of the period between 5 and 10 milliseconds, then v is equal to 0. So we need to be able to split this integral into two separate sections. The first is between 0 and 5 milli, and the voltage is just equal to 10. Then the second is between 5 milliseconds and 10 milliseconds, and the voltage here is 0. That means that this second part of the integral will always be equal to 0, so we can completely discount that, and we can just look at this area here, and this is the integral that we need to solve. So in this case, you can see that t is the entire period, so this stays at 10 milli, but we've lost the other side of the term because it was equal to 0, so this is still between 0 and 5 milli. So I can now solve this. And I get my minus 0 because this lower limit is 0, so the t becomes 0, the whole thing goes to 0. So all I need to do is calculate this. So my 10 cancels with my 10, and my milli cancels with my milli, and I'm left with 5 volts, which matches exactly the other method of doing it by using the areas. Now let's take a look at another example where you can't use the area to calculate the average voltage. This time we have something that is called a rectified sine wave. So it looks like a sine wave, but you just have the positive component that is repeating. So instead of the full sine wave that you normally see. So you can also see that the period here is half of what we normally have in a sine wave. So we want to work out the average for this, and we have to use integration. So we can use the formula that we've been using all the way through so far. So here we want to integrate between one period, which is one of these sine waves, to find the average. So there are a few things that we need to look at first. So now our axis, we're measuring time on the x-axis and voltage here. So we need to work out the function of v. And normally when we have a sine wave, we have y equals sine theta. In this case, we're measuring in terms of time rather than an angle. So we have to look at what function we normally give this. So in this case, v is the function. We're going to say a is the amplitude, so that's going to be the height here, the amplitude a, sine, and instead of a theta, we have this omega t. So omega is the angular frequency, and this is your standard wave function for a sine wave. So in this case, you can see that omega t is actually equivalent to an angle theta. This is important, and we'll use this result because here we have one period t, so we can say that this is going from 0 to t. And after this time period t, actually this is when theta would usually be at pi. So we have pi here and 2 pi. So actually when t is equal to big T, we get omega t is equal to pi. And this result is going to be important for us later, so we'll come back to that. So let's fill this in with the function that we now have. And you need to remember how to integrate a sine. So I can bring my constant, a is just a constant, I can bring that out of the front. And a sine will go to a minus cosine. You divide through by omega. And between limits t and 0. So if you're not sure where this omega has come from, then that has come from substitution. So you need to go and brush up on that a little bit. So this is now the expression that we need to substitute our limits in. And you need to remember what a cosine wave looks like. In here, I've put in cos 0 from the lower limit, and when cos is 0 here, then the cos is equal to 1. Now, what about this omega t? Well, that's where this result that we had earlier was really important. We had when omega t, when we have t equals the period, then this equals pi. So we can use this result here to plug into here. So essentially this becomes and we can substitute, so cos pi, we have a -1, and at 0 we have a +1. Again, now on the bottom line, we now have this expression here, and this is what we had here, which was equal to pi. So we can now substitute the pi into there. So the average of a rectified sine wave is always going to be equal to 2 multiplied by the amplitude, which is the same as the peak-to-peak voltage in this case, divided by pi. So that is your general solution for any waveform that looks like this with a certain amplitude. To calculate root mean squared or RMS values, we use the same method but slightly different equation. So if we go back to the definition for root mean squared, what we do is we take the y values, so you take your original function, you square it, then you calculate the mean of these squared values, and then you take that expression and you finally root it to get the root of the mean of the squares. So the full equation looks like this: the RMS is equal to the square root, and you're still doing the division by the x values and then the integral between your two limits, but the only difference is here that you have your y squared values instead of your y values. And don't forget that you will have to square root your final result at the end. So we're going to start with this waveform. So this is a sort of triangular wave or a sawtooth wave, but it's pulsed, so it actually has this this dead time in the middle where the voltage is equal to 0. So we're going to look at a general case instead of putting in fixed values for the peak-to-peak voltage. So in this case, the peak-to-peak voltage is equal to the amplitude if we set this here as 0. So this is VPP. And the time period goes all the way across until the waveform repeats itself. We'll put some more values in here, so actually we'll say that this triangular wave part only lasts for a quarter of the entire period, and then the voltage is equal to 0 for the rest of the 3/4 of the period. So let's start this calculation. This is the equation that we need to use. Instead of writing out the square root all of the time, I've just left the squared term on top of the RMS, but we do need to remember to square root our answer at the end. Of course, you can see here our one time period is split into 2 regions, so we need to split the integral into 2 regions. So this is split into 2 regions now. I have V1, which is the function here, and this part is equal to 0 because we're saying that this is the 0 volt position. So this term will always be 0, so I can discount that entirely, and I'm left with just having to calculate this. So of course the first thing that I need to do is work out an expression for the function V1 in this region here. Now we go back to our equation for a straight line, y equals mx plus c. The c value is the y-intercept, which you can see is 0 in this case. So we have y is equal to v, and we have x is equal to t, and c is equal to 0. So this is the expression, and m is the gradient, the change in y over the change in x. So the change in y is just VPP, and the change in x is t over 4. That means I can now rewrite the expression for V1 here. And don't forget that this function in here has to be squared, because that's your definition of the root mean squared. You have to square the values. And to solve this, I can bring out all of the constants to the front. And now I substitute these limits in after I do the integration. And now I can just simplify by cancelling some things. So you can see that the t to the 3 cancels here. This is 4 to the 2, so this cancels. So I'm left with VPP squared over 3 times 4, which is 12. And don't forget, this was the RMS squared. So in order to calculate the RMS, I have to square root this. So my RMS is equal to root VPP squared over 12, which gives me VPP over root 12. This can also be written as VPP root 3 over 6 if you wanted to tidy it up more.